Kia ora, guys. I've had a couple of questions now regarding doing the trig in 3D, so I thought I'd actually just go ahead and we'll go through one of the questions for you guys, okay? I thought that would probably be a bit easier, and it's easier than me trying to explain it to you on Teams, because I think that's quite confusing. So let's have a wee read through page 43 together, okay, of the Walker Maths book. So yeah, one word that has come into it that I didn't mention in our lesson the other day is a plane. Okay, a plane you can imagine as like a piece of paper. Okay, so it could be a square, it could be a triangle, but the idea is that it's flat. It's two-dimensional. Okay, a plane, it lies there flat. Okay. What we want to be able to do is deal with triangles that are part of three-dimensional objects. And so those triangles would be one plane, okay, or they'll sit on a plane. So it's like cutting out a triangle from a piece of paper. And they might meet other planes along the edges. Okay, or also at their corners. So for example, if I were, let's say I just redraw the cuboid that they've got on the book there. What's up with that corner there? Oh yeah, that's right. So if we have a wee look at the cuboid, that kind of example, they've done a triangle that's meeting down here at D. That's sort of the apex of it. It goes up here to F and down here to G. And so it's sitting inside this cuboid or this box. And so you have to kind of imagine it as a triangle that's been cut out of a piece of, let's say, cardboard, because it's nice and solid, and it's sitting there inside a tissue box, and it's got one corner wedged into this corner of the box there, and it's got its base, or this length here, FG, is lying along one of the lengths of the tissue box. Okay. So there's things that, if we have a wee look through that example, there's things that it talks about. So the first one is working out the length of DG. Okay, so you guys, I'm really hoping that you will have taken your time to read through that example on page 43. But yeah, we can do it together here. So we want to work out the length of DG. That was this green length here. So in other words, it's one side of this triangle that we're talking about. So you'll see that they say DG lies in a triangle, so it's part of a triangle, isn't it? This green triangle, and it lies on the floor of the cuboid. And so then you'll notice that they have redrawn the floor of the tissue box. Okay, let's just call it a box. They've redrawn that, so they've drawn the floor of the box. They're not at the moment talking about the green triangle, and they're not going to be using parts of the green triangle to work out what DG is. They're going to use the floor, because we know things about the floor. We know that it's 15 centimeters long and it's 8 centimeters wide, and we know that that line DG runs all the way across from the corner D over to the other corner G. Okay, you can see that that becomes a right angle triangle. So hopefully you can see that's why they can use Pythagoras there. Okay, so question one, once you redraw it, you can hopefully see that that's a nice easy Pythag question. So if you look at question 2, they then say, okay, calculate the length of DF. So we go back to our original cuboid and you find D and F, and that ends up being the other long side of your triangle there. Okay, it's that top one. Okay, so that seems to be running, it sort of runs right through the middle of the box, doesn't it? Okay, so you have a wee look, go, okay, so what triangle is that a part of? Well, the only triangle that it's a part of is that green DGF one. Okay, cool. Well, let's draw that and see what do we know about that triangle. So here it is there, DG. DGF? Well, we already know that we've got 6 centimetres. How do we know that that's 6 centimetres? Oh, yes, that's written on the thingy. So, yep, we've got 6 centimetres for FG. And you've just worked out in part 1 that that was 17 centimetres. How do we know it's a right angle? How do we know it's a right angled triangle? And so for this, again, if you imagine that you've cut out this triangle out of cardboard and it's sitting inside a tissue box, you could rotate that. It wouldn't fit. You'd have to cut the end off it. But if you rotate it and put it up so it's flat up against the end, like the edge, so you're looking down inside your tissue box, imagine that you rotate it so instead of going diagonally across, it runs flat up against the side. It would be a right angle. And what's happened is we've just rotated it out so that instead it touches the other corner. So it is a right angle in that bottom corner there. Okay, at FGD, that is a right angle. So that's why we can now use Pythagoras. Okay, and it does. You've got to use a bit of imagination, a little bit of three-dimensional thinking. And honestly, I wasn't joking when I said you might like to actually get a box at home and cut out shapes. That's totally no joke, because you won't be able to do that in the exam. But to do it now could actually be really, really handy. Okay, and it could help you. So yeah, part 3. So again, that was Pythagoras. You can do that. Working out the angle. So they say calculate the angle DF. The angle between the line DF and the plane DHGC. Okay, so when they say the plane, they're talking about that flat piece. Okay, and DHGC. So in other words, that's the floor, isn't it? Because we've got H here and C here. So they're talking about the floor. So they're saying, okay, you've got the floor, and we want to know the angle between the line DF. So that was that line that meet up there at F, and they want to know what's the angle that it makes with the floor when it touches the floor there. What is that angle there? So that's what they're talking about. And again, it's kind of floating in space. We're kind of half looking down onto it. Remember that the triangle, the bottom of it goes across to the other bottom corner there. So yeah, we're having a wee look at that. What is that angle there? So again, what we now do is we think, okay, so what triangle is that part of? All right, so that angle there, what triangle am I talking about? Okay, so I'm using that line DF. I want the angle of where that line meets the plane, the floor in this particular example. And so when I think about it meeting the floor, I'm thinking about it meeting its other edge, the other edge that ends up heading out there to G. So we are still talking about the original green triangle, aren't we? DGF. We know bits and pieces about DGF now. We know the 6 centimetres. We know the 17 centimetres. We want to know this angle. So we're going to use, we know that this is a right angle in there. It's very three-dimensional, guys. It's weird, I know. And so we can use some trigonometry there. Okay. Yeah, it's definitely... That's good stuff, this. It's good. Okay, let's look at number 4. The last question is the angle between the plane HFD. Okay, so let's look for H, F, and D. So let's use a different coloured pen. F to H to D. So if that makes a plane, that is a triangle. There's only 3 letters involved. So it is a triangle. You know how they call it a plane? That's where you can really imagine it being a piece of paper. And so I'm sort of colouring it in there because we're talking about like the whole area of that triangle. Okay, when they refer to something as a plane, they're talking about, you know, the whole thing, and you can imagine its area. So we're now talking about that blue triangle, HFD. So we'll just redraw it here. So we want to know the angle between this plane, HFD, so this triangle, and the plane DHGC. Now, DHGC was the floor, wasn't it? Okay, so H and D are part of the floor. So what we're wanting to know is this angle here, aren't we? and it runs all the way along. It's the angle, like if you had a hinge on a gate. It's, you know, how you can sometimes get those, when you have a gate, you can get those little triangular, let's say this is a gate here, you can get these sort of triangular hinges on the gate, and it swings open, and, you know, supports the gate on it. That's what you can imagine here. It's that angle. You've sort of slightly opened a big old rusty triangular, you know, hinge, and we want to know what's the angle that that triangular hinge makes with the wall or whatever where the gate was. All right, so we've got that hinge going where the gate is. I just had to pause everything for a while there. And so, yeah, we're wanting to know what is that that angle that it's being made. I'll just, oh, no, sorry, just ignore that. So you're really thinking about opening it up, as I say, like that gate. So if we look at the back here, we've got this line, HF. We've got that. That's exactly the line that opens up when the gate is opening. You know, it's that line there. This other angle from F, that other line from F down to D, that other edge, that angle's going to be a little bit trickier because it's not telling us exactly the bit from, I'm still on the rubber. It's not going to tell us the angle that we actually want to know, because we're wanting to know, you know, how far it's opened up. So if we go to that back triangle there, HFG, okay, so HFG is the one that we can use. We know lots of other bits and pieces, but that's what we want, because that's going to tell us this angle here of how far it's opened, So we can use the 6 centimetres for the FG and the 15 centimetres, because we know that's how long our base is of our box. And so therefore, again, we can use nice old trig. So yeah, hopefully that makes some sense, guys. It is challenging stuff, this particular one, but yeah, it's one that, like lots of things, needs a bit of practice, and we can spend a bit more time in class practicing this if we need to. Yeah, but just email me if you've still got some questions. Don't let yourself get stressed out if it's too hard, okay? We can wait till we're at school and I can explain it to you again at school if we really need to. Okay, all right, thanks guys. Look after yourselves and I'll see you at school next week.